Hello, you're welcome back. All right, so we're going to continue from where we stopped. We are going to be looking at the basic operation in Laplace transform. So the operation that we are going to be looking at is the scalar multiplication of Laplace transform function, the addition, subtraction operation, and some other theorems. Okay, so now let's start with the scalar multiplication. So when you have the Laplace transform of um, a constant multiplied by the function of t, so this is the same as a Laplace transform of the function of t. So it's like more like uh, what we do in integration. Take the constant term behind the integral value. That's exactly what is happening here. Okay, let's look at some typical example. Okay, so let's say you are being asked to evaluate the Laplace transform of 3 3 exponent of 3t. Okay, so this is the same as evaluating the Laplace transform. This is the same thing as multiplying 3 by the Laplace transform of the exponent of 3t. Okay, and of course, you know what the answer is. That's gonna be 3 into uh, the Laplace transform of exponent of 3t is 1. Of course, 1 all over x minus 3, which of course is 3 all over x minus 3. Okay, so I can also do more example, but this is actually enough. All right, so let's look at another operation, number 2. So Laplace transform of the sum or difference of a function. For example, the Laplace transform of f of t plus or minus g of t. Okay, so this is simply going to be the Laplace transform. This is equal to the Laplace transform of f of t, okay, plus or minus the Laplace transform of g of t, okay, g of t. So with this now, it is possible to evaluate the Laplace transform of a polynomial. For example, okay, let's say you're being given the Laplace transform of, let's say, t square minus 2t then plus 2. Okay, so it is very easy. So this is more like uh, okay, to solve this is very easy. This is more like doing evaluating the Laplace transform of t square minus 2 times the Laplace transform of t then plus the Laplace transform of 2. Okay, so of course this is equal to the Laplace transform of t square is 2 factorial all over s raised power 2 plus 1. You know that already. The Laplace transform of t is something as t raised power 1. Okay, that's gonna be 2 times of course 1 factorial divided by s raised power 1 plus 1, then plus the Laplace transform of 2, that is going to be 2 all over x. So we can actually solve this. Okay, so invariably now this is going to be equal to 2 factorial is 2 times 1 2, that's 2 all over x raised power 3. 1 factorial is 1, that's 2 all over x raised power of 2, then of course 2 all over x. Okay, so that is the answer to that. So please take note of that. All right. So now any other operation in Laplace transform is based on theorems. Okay. So the very first theorem we're going to look at. Okay, let's look at theorem 1. It's an operation. It's an operation. Okay, it is known as the first shift. First shift theorem. All right. Okay. So now this actually happens when you multiply the Laplace transform of a function, look at how it goes. If you multiply the Laplace transform of a function f of t by the exponent of at, so this is like more like the product of a function f of t then multiplied by exponent at. Okay, all right. So now this this is we end up yielding, the result is going to be f of x plus a. This is first shift, simply means that the result of the Laplace transform f of x will be shifted by addition of a, being of course being the a, all right, exponent of minus 80. This is this a here is what we are going to be using in this case. Now let's look at a typical example. For example, okay, the Laplace transform of the exponent of minus 3t then sine 2t. So we are using this as a okay, the shift to this Laplace transform. This right here is the actual f of t, then there's a shift. This is going to be, so invariably now what it simply means that whatever we have, the very first thing we're going to do, we'll perform this Laplace transform first. So solution, so we'll first perform the Laplace transform of sine 2t. Okay, of course the Laplace transform of sine 2t is going to be 2 all over s square plus 2 square, which of course is 2 all over x square plus 4. So now where is the shift? The shift simply means that, look at what I mean by shift. In place of f of x, which of course, in place of x, okay, in this f of x, we are replacing it with x plus a. And of course, you know what the a is, okay? What the a is actually in this case now, in this shift, that is a is 3. So invariably now, for us to now perform the Laplace transform of the shift, that is exponent of minus 3t of the sine 2t, okay, so this is going to be equal to 2 all over any place I see x, and of course any place I see x, I'm going to have x plus 3, so that's going to be x plus 3 square. So I'm replacing that by x plus 3 square then plus 4. So this is going to be equal to 2 all over, if you expand this, you're going to have s square plus 6x then plus 9 then plus 4. Okay, so of course this is going to be 2 all over, adding the like terms, 9 plus 4, that should give me 13. So that's going to be s square plus 6x then of course plus 13. So please take note of that. So that is the first shift theorem. I can actually bring more example. Okay, for example, okay, if you are being asked to evaluate the Laplace transform of the exponent of minus 2t of this function, okay, let's say t raised to the power of 3. So that is a shift. We apply the first shift theorem. Okay, so in this case, of course, solution, the very first thing we're going to do is to perform the Laplace transform of t raised to the power 3, which of course is 3 factorial all over x raised to the power of 3 plus 1, that is 4. Okay, 3 factorial is 3 times 2, that is 6 all over s raised to the power 4. So now applying the shift, the first shift, that is Laplace transform of the exponent of minus 2t, then t raised to the power of 3. Okay, so I'm shifting this by x plus a, so invariably this is going to be 6 all over the a is 2, that's going to be x plus 2 all raised to the power of 4. X plus 2 all raised to the power of 4. So I hope that is well understood. Now let's look at another theorem. Okay, so theorem 2. Okay, so theorem 2 is actually based on when the function is multiplied. Okay, remember theorem 1, we multiply the function by exponent of minus 80. So when we multiply the function, multiply by t, or okay, multiply by t and or better still, let's not just say, it's either we multiply by t or t raised to the power n. Okay, just the powers of t, that's what it means. So how do we perform such operation? Now look at the theorem. So when you have the Laplace transform of operation, then multiply by t raised to the power n. Okay, operation f of t multiplied by t raised to the power n. So in this case, what we are going to have as the Laplace transform is the derivative of the Laplace transform of the f of t. So we are going to find the Laplace, okay. First of all, we are going to find the Laplace transform of f of x. Then we find the derivative. Once you see prime means derivative. Okay, can we actually do that? Okay, so in this case, okay, this is just not t raised to the power n, just t. This is t raised to, we are starting with t raised to the power 1. Then we'll now extend it to t raised to the power of n. Just t raised to the power where the n is just 1. Okay, so that means we are having just first derivative of the Laplace transform of the function. Okay, let's illustrate that with an example. Okay, let's say a situation where you are being asked to evaluate the Laplace transform of t, then sine 2t. Okay, so first of all, what we do is to evaluate. So what we do is we evaluate the Laplace transform of sine 2t, which you know is 2 all over s square plus 2 square, which of course is 4. Okay, so now extending it to Laplace transform of t sine 2t. Okay, so what I'm going to do, I'm going to find the derivative of this with respect to x. That is going to be d dx of this function, of the function 2 all over s square plus 4. Of course, you know that this derivative, okay, we apply quotient. Is this a quotient function? We apply quotient rule. Quotient rule. I hope you can still remember quotient rule. Okay, where this is my v and this is my u. Don't forget the formula. Divide the x. Okay, remember the formula of that's dy dx is equal to v du dx minus u dv dx all over v square. Okay, so if you can still remember that. So let me clean it up. So we begin. All right, so we begin. So starting with v, which of course is s squared minus 4. Then the derivative of du with respect to the x, that is 0. So multiply by 0, then minus u, which of course is 2. Then differentiate s squared minus 4. If I differentiate s squared, I'm going to have 2x. Okay? Times 2x. Then all over v squared s squared minus 4 all square. So this is going to be, okay? So with what we have here now, this is going to be minus 4x, as you can see, then divided by s squared minus 4 all square. Okay, so you can decide to expand it if you wish. That's going to be minus 4x minus 4, oh please, the x, this is x. All right, okay, so that's going to be minus 4x. If you want to expand this, that's going to be x raised to the s square, the square of s squared, that's s raised to the power 4. Use 2 to multiply this and this. That's going to be 2 times minus 4 times s squared, that is minus 8x squared. Then minus 4 squared is 16. Okay, so that's the answer. Okay, so that's the answer. So the answer is minus 4x all over s to the power 4 minus 8s squared plus 16. So I hope that is well understood. So now the question is, how do we apply it with other powers, the higher powers? We will now have t raised to the power n. Okay, so what we have t raised to the power n, this is the general formula. The general formula is minus 1 raised to the power of n, then dx. Okay, the nth derivative d square ds raised to the power n of the function of x. Okay, so invariably now, if it was t raised to the power of 3 of f of t, so what you're going to do is that we'll multiply s minus 1 raised to the power of 3. Then we're going to do the third derivative. Okay, I hope you can still remember different degrees of derivative. The s raised to the power 3 of whatever function we have as our f of x. So we are going to actually practicalize this as we progress in the, okay, with more example. All right, so let's do that in the next video. So see you in the next video. Thank you very much.